Hello everyone, my name is KimEH. Let us start the presentation today. These are the lists of today's literatures. The first literature is about machine learning-based facial beauty prediction and analysis of frontal facial images using facial landmarks and traditional image descriptors. Introduction. The beauty industry has seen rapid growth in multiple countries, and due to its applications in entertainment, the analysis and assessment of facial attractiveness have received attention from scientists, physicians, and artists because of digital media, plastic surgery, and cosmetics. An analysis of techniques is used in the assessment of facial beauty that considers facial ratios and facial qualities as elements to predict facial beauty. Although facial attractiveness can be debated on its objectivity or subjectivity, recent empirical results support the idea that attractiveness is objective and quantifiable, which is achieved by measuring cross-cultural differences, brain activity, and cognitive psychology. In machine learning, several methods have been proposed to assess facial attractiveness by using these facial features. In this paper, a technique for assessing facial beauty based on facial proportion factors is developed, which is widely believed to be the gold standard for facial beauty. Research conducted in psychology and biology settles the problem by making a hypothesis of which facial features contribute to attractiveness. This paper aimed to predict the facial beauty of frontal images using machine learning techniques and traditional feature extraction methods. The proposed technique improves the performance of machine learning models on facial images through the fusion of facial landmarks and texture, color, and shape features. An ablation study is performed on the 19 ratios to find out the best performing combination of ratios called the feature set. The ablation study is used to find out which of the TCS features contributes to the prediction and how the model performance varies among each combination. Materials and methods. The following steps were used to predict the facial beauty score. These figure represents the block diagram of the entire process. First of all, extraction of facial landmarks, texture, color, and shape, TCS features. Secondly, extraction of best performing facial landmark feature set was done. And for the third, ablation study of TCS features were done. The data set used in this study is SCUT FBP 5,500, a data set that consists of 5,500 images of Asian and Caucasian males and females, where the dimension of each image is 350 to 350 pixels. The metrics used in this study to measure performance are Pearson's correlation coefficient, mean absolute error, mean squared error, and R2 scale. All the models are trained on the same dataset using Python 3.7 software. Facial ratios are calculated by measuring the distance between certain points on the face image. These points are called facial landmarks, which are coordinates on the face image. The SCUT FBP dataset contains predefined facial landmarks for all the 5,500 images. Each image had a total of 86 landmarks that covered the most important points in the face. These facial landmarks were used to calculate the 19 facial ratios used in this analysis. This figure illustrates the facial landmarks for the input sample image. The facial beauty rating for all the 5,500 images available with the dataset was used as a label for the 19 ratios. These ratios are used as input to the model for the prediction of facial beauty. The basic premise of the feature set is that certain proportions of the face should follow defined ratios. Here, 14 golden ratios and 5 symmetry values have been used. A total of 19 values are referred to as the feature set FS. To assess facial beauty based on facial portion features, 19 ratios in the FS are analyzed. A detailed description of the various ratios in the FS is given in Table 1 and 2. In Table 1 and 2, D refers to the Euclidean distance between landmarks M and N. The ratio values in the FS were different, so normalization had to be performed on the ratios. In the golden ratios, attractive faces should have a ratio of 1.618, and in symmetry ratios, attractive faces should have a ratio of 1 point. So, z-score normalization and linear scaling are used to normalize the ratio values into an interval of 0.1. The normalization formula is given by these followings. From previous literature, it is obvious that only facial landmarks and facial ratios cannot be used to provide good results when predicting facial beauty. This study aims to use facial shape, textures, and colors to predict facial beauty and infer the performance and contribution of features towards the performance of the model. These features are called a secondary feature set, or SFS, in this study, and the types of features extracted are as follows. GLCM, or Gray Level Covariance Matrix, is also known as the Gray Level Spatial Dependence Matrix, which learns about the texture of an image by calculating the frequency of pixel pairs with certain values in a spatial relationship that occurs in an image. GLCM features are extracted for this study as they provide good information regarding the spatial relationships in the image. The statistical descriptors and their description are provided in this table. Each statistic returns a single feature value for an image, and the 4 features of correlation, contrast, energy, and homogeneity make up a feature vector that is concatenated with the best performing FSSs given in the facial feature set extraction section. In this study, the FS is used as input to the models and the corresponding scores as the labels. Also, 4 well-known regression models, linear regression, LR, K-nearest neighbors, KNN, random forest, and artificial neural network were used for prediction. A small description for each model is given below. Linear regression is a statistical technique that uses several explanatory variables to predict the outcome of a response variable. It sets up a relationship between input variables and target variables, which is represented by the following equation. Random forest is a supervised learning algorithm that uses ensemble learning methods for classification and regression. Random forest is a bagging technique and not a boosting technique. The trees in random forest are run in parallel. There is no interaction between these trees while building the trees. A random forest is a meta estimator and which aggregates many decision trees with some helpful modification. K-nearest neighbor false is a lazy learning method, which means that there is no explicit training phase before classification. The Euclidean distance formula and probability formula of the KNN method are given in the following equations respectively. In ANN regression, a multi-layer perception is applied which is composed of an input layer, hidden layers, and an output layer. Each layer has one or more neurons directionally linked with the neurons from the previous and next layers. A sigmoid function was applied as the activation function to compute the output of the hidden layer in each neuron. To measure the model performance and calculate the error generated by the models, Four metrics are used: mean absolute error, mean squared error, R-score, and Pearson's correlation coefficient are provided in this table. The data set was split into training data 80% and testing data for 20%. All the experiments were run on an Intel i3 processor with 12 gigabytes of RAM using Python programming language. 2 ablation studies were performed. Result and discussion. In our study on facial beauty prediction, we used facial landmarks as a base feature set for extracting facial features. From the facial landmarks, we calculate 19 facial ratios that are used for predicting the beauty of the facial image. The analysis compared the performance of computer models against human ratings and examined the performance of each model. This table shows the performance of each model concerning their correlation and error metrics. In this table, each model has a relatively high correlation with human ratings and low errors for each of their corresponding best performing FS. For another result, KNN has the highest correlation values with the lowest error. ANN has a higher correlation than LR, but LR has comparatively lower error than ANN. Also, ANN is much more scattered than LR. The red line in the graphs shows the regression fit of the data. This feature 6 shows us how each model learns from each feature in the FS and how each feature contributes to the learning process. The x-axis in figure 6 represents the number of features used in the ablation study, and the y-axis represents the score for each metric. The x-axis starts from 4 because the metrics for feature 3 and below were very poor, and hence it was decided not to be added in the graph as it would be negligible in comparing the performance of the models. It is trivial from figure 6 by B when the model features is less for 5 and 6 in x-axis. The R2 is in a negative trend, which indicates that the fit with regression curve is worse. Meanwhile, by increasing the number of features, the R2 values are improved significantly. This table 6 and 7 shows the ablation studies performed for each model. It is observed from these tables the fusion of texture, color, and shape features as the SFS along with the ratio features improves the overall performance of the model. The highest correlation is achieved by KNN followed by LF. The least correlation is obtained through LR and ANN. Since the KNN model has achieved the highest correlation values and lowest errors, it is considered as the ideal model for facial feature analysis, and the obtained results are given in this table 8. It's about the images and scores of few best and moderate prediction results. From the above obtained results, it is clear that our technique has avoided overfitting in our study through the following ways. First, the dataset used is from SCUTFBP 5500, which is a collection of frontal facial images. This dataset has been extensively used by many researchers. There is no class imbalance, as shown from the histogram of figure 3. The dataset has an equal number of images of each class in the training and testing set, and the target levels are normally distributed. The data used is enough, and since it is already balanced, no pre-processing or data augmentation was required. Secondly, an ablation study was conducted to find the best performing feature set and to find the optimal number of features which can be used to achieve the best performance. We avoided overfitting by removing features and limiting the maximum number of features to 19. Conclusion. In this study, different computer models are analyzed to predict facial beauty using facial features like golden ratios, texture, shape, and color through machine learning. First, The models are analyzed and the performance of facial ratios is derived from golden ratios and symmetry. 19 facial ratios were selected to represent the feature set, from which the best performing features were derived by population study on each feature. From the best performing FS for each model, texture, color, and shape features were extracted from the data set. Our analysis has shown that human judgments regarding facial beauty are consistent with the facial ratios derived from painters, architects, etc. But there does exist the element of variation, which exists as secondary features like sexual features, facial health, etc. Our analysis has shown that combining secondary features like facial health, texture, and shape with facial proportions allows a computer model to learn better and correlate much more with its human counterparts. Overall, analysis has been limited with the facial beauty prediction of Asian and Caucasian males and females. Our future work will involve an analysis of facial beauty for different types of people. Alongside, our analysis will use more powerful algorithms to extract the deep features and use the same fusion technique on those features to achieve an even higher correlation and error. The second literature is about facial aesthetic concern is a powerful predictor of patients' decision to accept orthodontic surgery. With reasons often unknown or misunderstood, some patients with pronounced skeletal malocclusions and altered facial aesthetics refuse orthodontic surgery suggested by orthodontists. Orthodontists suggest orthodontic surgery based on the severity of the skeletal malocclusion. There are no clear indicators for choosing orthodontic surgery over the camouflage treatment. According to the literature, factors that may influence patient decision-making process range from psychological factors, personality characteristics, facial morphology, patient motives, time availability, and financial resources. In addition, one of the aspects that could influence patient decision to accept or decline surgery is the perception of their facial appearance, which varies and is influenced by different factors such as sex, age, marital status, socioeconomic status, occupation, and the influence of family, peers, colleagues, media, and cultural aspects. Orthodontic surgery has been studied thoroughly, with reasons to undergo this treatment relating to physical appearance and functional ability. But factors associated with patient motives to decline surgery are lacking comprehensive research. One study investigated explanatory factors to decline this treatment to be possible consequences like nerve injury, which will lead to a prolonged burden on the patient to care and seek further medical treatments. Other factors may be due to general reluctance to surgery, reluctance to orthodontic treatment, and patient's perception that their bite was not particularly severe to require surgery. In the current literature, no predictors have been identified regarding orthodontic surgery acceptance. Therefore, the aim of this study was to investigate which dimensions of quality of life are affected in subjects with skeletal malocclusions in comparison with those without malocclusions, and to identify factors influencing patients' decision to accept the suggested surgery. Patient perceived factors were analyzed, while controlling for demographic factors and normative level of treatment needed. Materials and methods. This paper was designed with cross-sectional with stratified sampling, 190 Caucasian subjects aged 17 to 46 years. 95 subjects were consecutive patients referred to university dental clinic for skeletal malocclusion treatment, of which 58 subjects accepted suggested surgery, 37 refused. The other 95 were age and sex-matched controls without malocclusions, recruited recruited from the pool of students and employees of local high schools and university. Psychological and functional issues were evaluated by orthogonal quality of life questionnaire. Complexity of malocclusion and treatment need was assessed by the index of orthogonal functional treatment need. Results. Age and both genders were equally distributed among the three study groups. Among subjects with skeletal malocclusions, there were 60% with class 3, 23% with class 2, 26% with open bite, and 16% with asymmetry. No significant differences were observed between those who accepted and refused surgery. A positive linear correlation between IOFT and grades and OQLQ dimensions, except awareness, was detected. Awareness had a moderate effect size, while the other had a large effect size, the largest FA. There were significant differences in OQLQ dimensions between IOFT and grades, with moderate to large effect size, mainly with grades upper than 4 having much higher values than grades 3. A positive linear correlation between IOFT and grades and OQLQ dimensions, except awareness, was detected. All OQLQ dimensions differed significantly between the three study groups. AW had a small effect size, while the other had a large effect size, the largest FA. People who opted to orthogonal surgery had the highest AW, FA, and the most disturbed OF and SA, while the control group had the lowest. People with skeletal malocclusions who refused surgery had significantly lower aesthetic concerns, functional problems, and aesthetic awareness than those who agreed to surgery. Discriminant analysis demonstrated that in the terms of quality of life, the three groups were significantly discriminated by characteristics that combined aesthetic concern, oral function, and social aspect in function 1. The subjects who accepted surgery are considerably distant on the x-axis from the control group without skeletal malocclusions. Group that accepted surgery is characterized with the highest aesthetic concern, impaired oral function, and disruption of social contacts, while control group with the lowest values in these dimensions. In univariate logistic regression analysis, the odds of accepting orthogonal surgery are 3.4 higher in people with high facial aesthetic concern compared with those with low facial aesthetic concern. When controlling for age, sex, oral function impairment, awareness of facial deformity, and inhibitions in social contexts in multiple logistic regression, both IOFTN and FA remained significant predictors of orthogonal surgery acceptance. Discussion. Current research demonstrated that patients with pronounced skeletal malocclusions had all of their quality of life domains altered. This research shows the relationship between clinical norms for orthogonal treatment need based on IOFTN index and self-reported quality of life is not completely linear. It seems that the boundary is IOFTN grade 4 and that higher grades mostly induce significantly higher awareness of facial deformity, aesthetic concern, disturbed social interactions, and more functional limitations than lower grades. Differences among lower grades are minor. Recent studies emphasize that physician pain as well as psychological discomfort and disability were the most common oral impacts in malocclusion patients before treatment. Our findings are in accordance with novel researches that confirm facial aesthetics to be considered as the main motivational factor. This is explained by increased interest in facial aesthetics and dissatisfaction regarding appearance in young people. This study also showed it is more likely that people with high facial aesthetic concern will accept orthodontic surgery. Appearance is a subjective perception that varies between individuals and also varies with regard to importance. It demonstrates that orthodontists are highly aware of facial deformities when compared to patients whose range of acceptable facial characteristics is clearly much broader than the norms. Discriminant analysis demonstrated that in quality of life, three groups differed mostly in facial aesthetic concern, followed by altered oral function, then by social interactions, which are the highest in the group that accepted surgery. As a clinical implication, we wanted to emphasize the use of OQLQ questionnaire routinely as part of first consultation with orthodontic patients. While orthodontists clinically diagnose the skeletal problem, using this standardized questionnaire provides us with useful information of patients' own perception of their condition. There are some limitations associated with this study regarding convenience sample and its heterogeneity. And even though we did report distribution of specific types of skeletal malocclusions, homogeneous sample is recommended as it could reduce questionnaire discrepancies. It is widely accepted that oral function and facial appearance are affected in patients with skeletal malocclusions. However, we may now accept that patients choose surgical treatment to improve facial aesthetics rather than their disturbed oral functional problems. Conclusion. Facial aesthetic concern is a very important factor in patients' decision-making process for accepting orthodontic treatment for skeletal malocclusions, with greater importance than high normative need for functional orthodontic treatment. Furthermore, facial aesthetic concern is a prominent patient perceiving factor in the decision-making process to accept or refuse orthodontic treatment for skeletal malocclusions, with greater importance than high normative need for functional orthodontic treatment assessed by the orthodontist. Let's move to the third literature. Third literature is about tracking cortical representations of facial attractiveness using time-resolved representational similarity analysis. When we see face, we almost immediately can tell whether we find it attractive or not. Beyond such first impressions, facial attractiveness affects people's everyday lives in fundamental ways. Given these varied effects of facial attractiveness, a large body of research has focused on understanding the factors that make a face attractive. How does the brain achieve the transition from physical stimulus properties into an individual representation of facial attractiveness? To answer this question, previous studies have used event-related potentials obtained from EEG recordings to investigate when brain responses to more or less attractive faces differ. Although in many such studies, facial attractiveness influences multiple ERP components, a key question is when facial attractiveness is first represented in EEG signals. Given these mixed findings, at which time do brain signals first reflect face attractiveness? One factor that complicates the interpretation of previous studies clearly is the variety in tasks, with some studies employing explicit attractiveness ratings and the others employing orthogonal tasks, which makes it hard to appreciate whether. Here, we set out to resolve when cortical representations of facial attractiveness first emerge during an explicit attractiveness judgment task. By using multivariate representational similarity analysis on EEG data recording during this task, we were able to temporally track the emergence of representations of facial attractiveness with high sensitivity, while at the same time being able to control for other sources of variability in the faces. We found that already between 150 and 200 ms of processing, brain representations affected facial attractiveness. Results. We asked participants to rate the attractiveness of 100 male and female faces. Stimuli were highly controlled full front face photographs taken from the Face Research Lab London Set 41. Eliminating many sources of visual variability. On every trial, participants saw one of the faces for 1.450 meter per second and subsequently answered two questions. On the first question, they indicated whether they found the face attractive or not. On the second question, they indicated how attractive they found the face on a 1 to 7 scale. We compared the participants' attractiveness ratings with ratings from a large group of observers. Both the database ratings and responses collected during the experiment showed reasonable variance across the faces. To measure how brain signals differed between faces of different perceived attractiveness, we recorded participants' brain activity using a 64-channel EEG system. We analyzed EEG signals using time-resolved multivariate representational similarity analysis. To investigate when cortical representations carried information about facial attractiveness, we modeled each participant's neural RDMs using 3 predictor RDMs. Full details on the predictor RDM construction can be found in the Materials and Methods section. Early cortical representations of facial attractiveness. Correlating the predictor RDMs with the neural RDMs for each 50 ms time being across the epoch, we obtained a time series of how well EEG response patterns were predicted by facial attractiveness as defined by the 3 predictors. Information about facial attractiveness was obtained for widespread temporal clusters across the EEG epoch and for all 3 types of predictors. Are neural representations of facial attractiveness explicable by average preferences emerging across a large group of observers, potentially driven by a fixed set of physical face properties with inter-individual variability reflecting merely noise? Or do they partly reflect idiosyncratic preferences, that is, an individual person's unique aesthetic preferences for particular faces? To resolve this question, we performed an analysis where we modeled neural RDMs as a function of individual yes or no responses and attractiveness ratings, while controlling for the database ratings using partial correlation analysis. We found that individual attractiveness judgments still significantly predicted cortical representations, both when considering yes or no responses. In the first analysis, we tested whether other high-level face attributes that depicted person's sex, ethnicity, or age could explain the different cortical responses to faces of different attractiveness. To do so, we modeled the neural RDMs using 3 predictor RDMs. First, a predictor RDM that modeled the faces' dissimilarity in sex. Second, a predictor RDM that modeled the faces' dissimilarity in ethnicity, and a predictor RDM that modeled the faces' dissimilarity in age for details, same materials, and methods. Each of these high-level attributes predicted parts of the neural representation across time. 6 predicted face representations from the 100 to 150 ms time bin. In the second control analysis, we controlled for a variety of visual features analyzed during face recognition by a deep neural network, DNN. DNNs are the current state-of-the-art for modeling visual representations emerging in different processing stages of biological vision. Here, we use the DNN trained on recognizing faces, which has previously been shown to accurately approximate features analyzed during cortical face processing. We extracted predictor RDMs from the 16 convolutional layers of the DNN, in which each entry reflected the pairwise dissimilarity between the layer-specific activation vectors for two faces. These RDMs predicted cortical activation starting from the 50 to 100 time beam and in line with previous reports. Early representations were better captured by early DNN layers, while later representations were better captured by late DNN layers. Detailed results for all DNN layers can be found in supplementary figure S2. Next, we again modeled the neural representations as a function of individual yes or no responses and attractiveness ratings, but now controlling for features extracted in each of the 16 DNN layers using partial correlation analysis. Discussions. Using time-resolved representational similarity analysis on the EEG data, we reveal representations of facial attractiveness after 150 to 200 ms of cortical processing. Interestingly, we show that these presentations are related to individual participants' personal attractiveness judgments, suggesting that already early perceptual representations of facial attractiveness convey idiosyncratic attractiveness preferences. Further, we show that these early representations are genuinely related to attractiveness, as they are neither explained by other high-level face attributes such as face, sex, or age, nor by features extracted by an artificial deep neural network model of face processing. Together, our results demonstrate early, individually specific, and general representations of facial attractiveness, which may underlie fast attractiveness judgments. This is the end of my presentation today. Thank you for listening.